So what does Newton's second law tell us? It tells us that the net force in a certain direction, that's the total force in a particular direction, left, right or up, down, equals the mass of the object multiplied by the amount of acceleration in that direction. Let's have a go at using it to put some equations together. So the book on the table, obviously we're going to be using up, down, left, right as our directions, and we consider those two F equals MAs differently. So the F equals MA left and right, well, that's nothing's happening left and right, so we don't have to bother with that one. Literally nothing's happening. The F equals MA up and down, and in the brackets you put what you're doing, up and down or left and right, to show the examiner and yourself what you're doing. So you look up and down, and what we're going to look for is the net force in this direction. We're going to put that equal to the mass of the book, which is m, times the acceleration of the book. Now what is the acceleration of the book? It's not accelerating, the acceleration is 0. Right, so F equals 0 then, because it doesn't matter what the mass is, the acceleration is 0. Now normally it really matters that I go in the direction of the acceleration. So in this bracket you put the direction of the acceleration, which direction is it accelerating in, so that you know that that's positive and the other way is negative. In this case the book isn't accelerating, so it doesn't matter what I call positive and what I call negative. So I'm just going to say that up is positive and down is negative, but you could equally say down is negative and up is positive. It doesn't matter, as long as you stick to it. So up is positive, so up I've got R, that R is pushing the book up, and then minus down I've got mg. R minus mg equals 0. Now this makes sense, because if I put the mg on the other side, mg equals R, or if I'd done it the other way round, if I'd said down is positive and up is negative, that would have given me mg positive minus R equals 0. And these are all the same, obviously. So that's R is positive, up is positive, down is negative, up is positive. As long as they're opposite signs, they're going to give you this equation here, mg equals R, which makes sense because the book is neither flying up into the air nor is it sinking down into the centre of the earth. So that means the forces that are acting in this direction to push it up must equal the forces going in this direction to push it down. So one way of thinking about an object which is not accelerating is that the forces balance. The forces up equal the forces down, the forces left equal the forces right. But we are still just using F equals ma really, but with an acceleration of 0. The dog driving a car, we've got left, right and up, down. So let's look at those separately. Let's look at up, down first actually, because there's no acceleration in the up, down direction. So I'm going up and down and there's no acceleration, so I'm going to say F equals 0. So that means that the net force is completely balanced. All of the ones going up equal all of the ones going down. So I can choose this as being positive and this as being negative, and that would give me R minus mg equals 0. Or you can think of it as the force is balancing, so all the up equals all the down, and write it as R equals mg. Either of those equations. Okay, now let's look at our left, right. Now when we do our F equals ma, we're going in the direction of the acceleration, which is this way. So that is going to be my positive direction, and the other direction, the opposite direction, is going to be negative. So looking at my picture, what have I got going in this direction? I've got x, and then in the opposite direction, F, but that's opposite direction, so negative. So this is the net force in the direction of the acceleration, and that will equal the mass, m, times the acceleration, a. So now I've got these two equations, and usually what happens at this stage is that we do simultaneous equations to solve them. But I'm going to do that in a later video. This is just how to set up your equations from your resolved force diagram. The Hoover now, we've got left, right, up, down again. I'm going to start with the up, down because there's no acceleration in that direction. So F equals ma, ma is 0, so F is 0. So all of the forces up and down balance. They total 0, nothing's happening up and down in terms of acceleration. I'm going to take up to be positive and down to be negative. Let's have a look what's going on. Well, up, I've got R, that's going to be positive, and then down, I've got 2 going down. because I resolved that force, and you can see now why it is so important to resolve this force x, this diagonal force, into its left-right component and its up-down component, because now I can see I've got two forces going down, so they're both going to be negative, minus mg and minus x sine alpha. That's going to equal naught. If you prefer to think of it as the forces balance, because there's no acceleration, then the up equals the down, and so we'd get the equation r equals mg plus x sine alpha, which is obviously the same, just a different way of thinking about it. Okay, what about left and right? So we've got some acceleration in this direction. I should have put in here that I was going up and down. I'm going this way. That's my positive direction, and that's my acceleration direction, so I'm going to use that as positive. Now that means that I need to put my x cos alpha here. That's the only force going to the right. That's going to be positive, and my F for friction, that's going to be negative. I'm going to put that on the left. So that gives me x cos alpha minus F equals the mass times the acceleration. The mass is m, the acceleration is a. I end up with these two equations, which I'll end up doing simultaneous equations with. The confusing thing is having friction involved, is that we're using F for friction and F for resultant force, which is not great. So sometimes I like to use a little r next to the F to show that that's friction, not a resultant force. Okay, I probably won't bother with the left-right in this example, given that nothing's happening left and right, and you're presumably happy with that, so we'll just look at up and down. So I'm resolving in the direction of the acceleration, which is downwards. So I've got all of the ones going down are going to be positive, and all of the ones fighting them in the other direction are going to be negative. So what have I got going down? I've got mg, that's the weight of the fish, and I've also got x, which is the force coming from them swimming downwards, and then negative going in the opposite direction, so negative is t minus t. That's all the forces in that blue direction up down, and that equals the mass of the fish times the acceleration. Again, in this example, we've only got up and down movement, so I won't bother thinking about left and right. If I think about the cat in the balloon as one object, just the cat balloon, as being modelled as a particle, and use F equals ma in the direction of the acceleration, so up is positive, then I've got t going up, and then minus going down, I've got mg, that's a big M, so this is cat plus balloon as one object, and that will equal the mass times the acceleration. Now if I just think of the cat on its own, just imagine the cat. What does the cat feel? Well, the cat is standing on the bottom of the balloon, and like this, and it's got its weight going down, and it's got a normal reaction to the contact between the cat and the balloon going up. That's the forces it feels. So it doesn't feel a tension it doesn't feel itself being pulled up by anything, it feels itself being pushed up by the reaction with the floor. In total, it's accelerating upwards, so we say we're doing F equals ma in this direction, where up is positive, so up we've got r, and down we've got mg, and that equals the mass of the cat times the acceleration of the system, which would obviously be the same as this acceleration here, but the masses would be different. Let's start the car and the truck just by looking at the truck. Let's do that first. So just truck. Now we can use F equals ma, up and down or left and right. So let's have a look first of all at up and down, since there's no acceleration in that direction. Up and down. So if we're the truck, if we do F equals ma, up and down, there is no acceleration up and down, so that's just saying that the resultant force in that direction is 0. So all the ups equal all the downs. Well, we can see from our beautifully resolved diagram that going up we've got a reaction force, and going down we've got mg, big M, put big M for truck, and we've also got going down t sine alpha from the resolved diagonal force, and that's going to equal 0. Or we could think of it as all the ups are 1 equal all the downs, mg and t sine alpha. Either of those ways of thinking about it is fine. Okay, we've also got for the truck F equals ma left and right, and in that direction we do have acceleration. The acceleration is going in this direction here. Now, for the sake of just explaining things and showing examples, I'm going to say that this is moving with a constant velocity. So what difference will that make? Well, if something's going with a constant velocity, then its velocity isn't changing. If its velocity isn't changing, then it has no acceleration. Its acceleration is 0, and we actually have the same situation. We have F equals ma in that direction, but the acceleration is 0. So actually, we have that the net forces left and right equal 0 as well. So let's have a look at them under the blue line. Well, we can choose which way we choose to be positive and which way we choose to be negative. So I will choose x to be positive, and I will choose the other way backwards to be negative, so minus that friction and minus t cos alpha, and this equals the mass times acceleration, which is 0. Or alternatively, think of it as left equals right, no acceleration in this direction, so x equals f1 plus t cos alpha. So constant velocity means no acceleration. Okay, now let's look at the car. At this stage, you might be getting the idea and might want to pause this video and have a go at these yourself. Car, F equals ma left and right. There's no acceleration, so the total force is 0. That means all the lefts equal all the rights under this blue line. So that is t sine alpha equals f2. That's all that's going on. And then F equals ma, up and down. Well, again, I've got constant velocity, so I've got no acceleration, so the net result is going to be 0, which means that all the ups, t cos alpha plus r2, equals all the downs, mg. And then we would do simultaneous equations using these two, being very careful about what's the same and what isn't the same. If there was acceleration, which there isn't, but if there was acceleration, that would be the same. The tension in the tow bar here is equal to the tension in the tow bar here, but the reactions and the frictions would be different. How exciting, our first one on a hill. So let's do parallel to the hill first. So we're doing F equals ma, and we're going up and down the hill, and I'm going to do the double-headed arrow for acceleration in this direction because that's the positive direction. So everything going up the hill that way is going to be positive, anything going down the hill the other way is going to be negative, and that will equal the mass times the acceleration. So what have we got going on under there? Well, going up we've got t, then that's the only positive thing. Then negative in the opposite direction, we've got mg sine alpha, and we've got f. So they're all negative, and that will equal F for friction, so maybe I'll put fr, and that will equal the mass of the block times the acceleration. That's one of our equations. Now let's look in the other direction. F equals ma, away from the hill and into the hill. This is perpendicular to the hill now, so we're looking in this direction here. Now in this direction here there is no acceleration, which means that F equals 0, which means that all the ones going into the hill are equal to all the ones going out of the hill. So having a look at it in that way, we've got r, that's the only thing going perpendicular away from the hill, equals mg cos alpha, that's the only thing perpendicular into the hill, and then that's our equation. And then these two we can do simultaneous equations. The penguin! I like this one. Okay, let's start by looking perpendicular to the hill. F equals ma, perpendicular to the hill. There is no acceleration in that direction, so the net result is going to be 0. All the things going away from the hill equal all the things going into the hill. So away from the hill I've got r, and that's it. And that will be equal to the thing going into the hill, mg cos alpha. Done. Okay, what about F equals ma, and now we're going parallel to the hill, up and down the hill. Now we've got acceleration in this direction, so I'm going to make that really clear when I write this down that I understand the acceleration is in that direction, so that's my positive direction. So the mg sine alpha is definitely positive. That's the one going down the hill. Oops. Underneath here, mg sine alpha, that's positive. Now there actually isn't anything negative. There's nothing fighting that mg sine alpha. That's why the penguin's going so fast and getting faster. He's going shooting down. There's no friction because he's on ice and he's got a nice smooth belly. So mg sine alpha is the only thing featuring in this equation, and that is going to equal the mass of the penguin times the acceleration of the penguin. And actually we could simplify this, couldn't we, by cancelling an m off both sides. So the acceleration will be g sine alpha.